Thanks for tuning in. This presentation was put together and narrated by myself, Michael Genin, on behalf of Advanced Industrial Refrigeration. This is basically an introduction to refrigeration, and it will be a brush up for those who already know a little bit refrigeration. It also helps to internalize and get a better grasp of the refrigeration cycle. We'll then follow up with some practical examples at the end with real world component identification and real life examples of common HVAC equipment in the field. In this presentation, we will discuss what is a refrigerant and different refrigerant types. We will go over the vapor compression cycle and its key components. I'll focus on the expansion device, as I believe this is the key to the whole system and rarely properly understood. We'll talk about different types of compressors, different compressor technologies found in common HVAC equipment. We will look at different types of heat exchangers for evaporators and condensers. We'll follow up with practical examples of HVAC equipment, go over identification of the components, and the intent is for you to be able to approach this equipment in the field and identify the components for yourself. We aren't going to go into the whole history of refrigeration in this presentation. All I will say that it is a life-altering technology. Most of us think of electricity, the light bulb, farm mechanization, or the internet as being life-altering, but refrigeration is certainly on par, if not superior in my opinion, to many of these creations. It has increased our availability of food and allows us to sustain our lifestyle and population density. This photo was just a glimpse of how things were before refrigeration. People here are ice harvesting. Ice was taken from frozen lakes. It was stored in barns with straw, packaged, then placed on a nearby train, where it was delivered across the country. Put in another way, without refrigeration, large cities would not be able to exist. High-rise buildings would not be able to exist. Refrigeration has truly transformed society and increased our quality of life. So what is refrigeration? This is the typical definition. It's similar to ASHRAE's definition, and it means cooling a space, substance, or system lower or to maintain its temperature below the ambient one. And we typically think of refrigeration in these terms as some kind of cooling effect. Energy in the form of heat is removed from a low temperature reservoir and transferred to a high temperature reservoir. And this is really what I want you to think of when we think of refrigeration. It is a movement of heat from one reservoir to another. And it's not so much focused around the cooling effect. Most people think about the cooling effect, but it's important to think of refrigeration as the movement of heat from one area to another, because refrigeration can also be used as a means of heat production, not just cooling. Before we jump into the vapor compression cycle, we need to understand what a refrigerant is and what it does. Most people think of refrigerants as some kind of mysterious chemical, but they really aren't. Like any substance, they can exist in three states: a solid, liquid, and gas. Almost any substance can be used as a refrigerant. In fact, water can be considered a refrigerant. Ammonia is often used as a refrigerant. Propane and CO2 are also used as refrigerants. For this presentation, when we say refrigerant, let's keep it simple and just think of water. In the refrigeration process, the water will exist as a liquid or gas. We won't talk about it existing as a solid because that will cause major issues for what we're trying to achieve. When heat is added, the temperature of the liquid rises, and once it reaches its saturation point, it begins to boil or evaporate from a liquid to a gas. At this time, heat is added, but the temperature remains the same, about 100 degrees Celsius in the case for water. Heat continues to be added, but the energy is going in towards changing the state from that liquid to gas. During this process, there's a combination of both liquid and gas refrigerant but this is known as a saturation point. Temperature remains constant. Conversely, when we have a gas and heat is being removed, the gas changes back into a liquid through condensation. Heat is rejected, but the temperature remains constant during this condensation process as well. During the process of evaporation and condensation, a lot of energy is absorbed or rejected. And this is precisely what we need in our refrigeration system. The amount of degrees above the saturation point is known as superheat, and the amount of degrees below the saturation point is known as subcooling. We'll review these terms later on. This simplistic graph is for water with an evaporation point of 100 degrees Celsius. But let's say we wanted this evaporation to occur at a lower temperature, more optimized towards a conventional HVAC system used for comfort cooling, let's say 5 Celsius. We would need to lower the operating pressure of this system to about 1 kilopascal. This is fundamentally what is happening within the vapor compression cycle of the HVAC system. We manipulate the operating pressure to absorb heat at a cold temperature suitable for cooling. Then we manipulate the pressure to reject heat at a hotter temperature, typically the outdoor ambient. This is how we are able to move energy from a low temperature reservoir to a high temperature reservoir. In this chart, we have a list of the most common refrigerants which have been used in the HVAC equipment over the years. R11 and R12 were frequently used, and then we realized that when released to the environment, they contributed to ozone depletion and a hole in the ozone layer. We moved on to R22, R123, which were an improvement, but these too have been phased out due to their ozone depletion potential. We moved on then again to 134A and 410A, and we realized that these are greenhouse gas products and they contribute to climate change. So we are currently in the process of phasing out these refrigerants as well. Moving forward, the future looks like it will involve new HFO or olefin refrigerants, or a blend of olefins with some kind of older refrigerant. The bottom line is, when we say refrigerant, it's not some magical chemical. Think of water. The refrigerants behave in the same exact way of water. They just have a different boiling point optimized for a particular application. Water is denoted as refrigerant R718. These refrigerants are typically used in HVAC applications. There are other refrigerants that are better optimized for low temperature applications like refrigerators and freezers. Ultimately, when we choose refrigerants, we need to balance the ozone depletion, global warming potential, and their theoretical efficiency. We can keep choosing refrigerants which are lower and lower global warming potential, but if they have poor efficiency, the system will consume more power, which will ultimately create more greenhouse gases. Frankly, many refrigerants were used for non-HVAC applications like spray foam insulation and aerosols over the years, and these are a one-time use product, and these refrigerants were used to propel foam or the spray can product. HVAC is a small portion of the overall refrigerant use globally. So when choosing the correct refrigerant for the HVAC industry, power consumption or the efficiency of the cycle needs to be considered over the life of the equipment. We are now ready to talk about the vapor compression cycle. This diagram represents the physical system, and there are four main components that will be identified, which we'll get into. And I like to draw the cycle with this layout. This horizontal line represents the division between high and low pressure. Everything above this line is high pressure. Everything below this line is low pressure. Recall that we discussed manipulating the operating pressure of the system to adjust the evaporation and condensing temperature of the refrigerant. This vertical line represents the division between a gas and a liquid. Everything to the right of this line is a gas, and everything to the left of this line is a liquid. This means that there are four main conditions in which the refrigerant exists: a high pressure liquid, a high pressure gas, a low pressure liquid, and a low pressure gas. The condenser and evaporator are heat exchangers that transfer heat in and out of the refrigerant to some other medium, typically air or water. And we'll talk about different types of heat exchangers later on. The cooling effect is developed in the evaporator, and the evaporator removes heat from the heat load represented by the flame. The refrigerant travels through the evaporator. It evaporates or changes state from liquid to gas. The compressor, which is a mechanical device that's typically driven with an electric motor, it works with a vapor. It doesn't work well with a liquid, as a liquid will damage the compressor. The compressor sucks the vapor or gas out of the evaporator, and it compresses it to a higher pressure gas. This high pressure gas enters the condenser, where it changes back from a gas into a liquid, but this time at a higher temperature than what it did in the evaporator. Because the pressure is higher in the condenser, the refrigerant changes state at a higher temperature. This heat is rejected to some medium, water, or perhaps the outdoor ambient, and it's represented by the fan in this case. At this point, the refrigerant is condensed back into a liquid, and it exits the condenser. Next, we have the expansion valve, and this is probably the most important part of the system and also the most overlooked. Refrigerant is forced through a small opening inside the valve where the pressure drops from the high side to the low side. And when this happens, the refrigerant expands rapidly and it changes from a liquid to a gas, or some mixture of liquid and gas. Think of it like using a can of hairspray. The hairspray exists in the can as a liquid under high pressure, but when it's used, the hairspray is released to the lower pressure, or the room pressure, and it changes immediately from a liquid to its gas state. We're now ready for the pressure versus enthalpy diagram. Think of enthalpy as energy. This graph represents what is happening to the refrigerant inside the physical system. This graph has a type of dome which exists for any substance, even water. Everything to the left of this dome is a liquid, and everything to the right of this dome is a gas. Inside the dome, the refrigerant exists as a mixture of both gas and liquid. The line for the dome represents the saturation point between liquid and gas, or gas and liquid. The evaporation of the refrigerant happens from point 4 to point 1. This is where the cooling effect occurs. Heat, or enthalpy, is added to the system, and the energy is being used to evaporate the refrigerant from a liquid to a gas. During the time through the evaporator, pressure is theoretically constant, although in reality there is some pressure drop that exists through the evaporator as the refrigerant flows through the passages in the heat exchanger. The cooling load is the heat absorbed, or the horizontal distance from point 1 to point 4, multiplied by the rate of flow for the refrigerant. Gas then enters the compressor at point 1, and this is known as the suction of the compressor. People often refer to this as a saturated suction pressure. At this point, everything has been converted into a gas. The gas enters the compressor where it's compressed to a high pressure from point 1 to point 2. And note that the energy used to drive the compressor is the horizontal distance from point 1 to point 2. And this is known as the heat of compression. So why do we want to raise the pressure? Recall that raising the pressure allows us to raise the temperature at which the refrigerant changes state between liquid and gas. Having this at a higher pressure allows us to reject heat at a higher temperature to the ambient, for example. The hot discharge gas of the compressor, point 2, enters a condenser where heat is removed from the condenser and the refrigerant begins to transition from a liquid until it hits point 3. Note that the total heat of rejection is a horizontal distance from point 2 to point 3. The heat of rejection is equal to the sum of the cooling load plus the heat of compression. In other words, the condenser needs to reject the heat absorbed by the evaporator and reject the heat from the power input of the compressor. At point 3, the refrigerant exists as a high pressure liquid. The liquid enters the expansion device. This is where I find there's a lot of confusion about refrigeration, so I'm going to spend a little extra time talking about the expansion device. Let's think of an aerosol can, again like our can of hairspray. The can is full of a high pressure liquid, and when you press the valve, the liquid exits through the nozzle where it expands, and this expansion causes the liquid to flash and become a gas or some mixture of gas and liquid. It might not become fully 100% gas. It typically ends up becoming a mixture of gas and liquid, and that's why you see water droplets. So back to the pH chart, no energy is added or removed at the expansion valve. So the process is a straight line vertically where there is no change in enthalpy. Point 4, we exit the valve, we are inside the dome, and there is a mixture of gas and liquid refrigerant. But it's mostly liquid at this point because we can see that point 4 is a little closer to the liquid saturation than it is the gas saturation point. And this cycle continues back through the evaporator. So what's the purpose of the expansion valve? And many textbook definitions are the purpose of the expansion valve is to control superheat. So what is superheat? At point 1, we are exactly at the saturation point between a gas and a liquid. If we have any remaining liquid at this point, it can enter the compressor and it can damage it. The droplets entering the compressor can cause damage to the impeller, and this will be no good. So point 1, we call it the saturated suction temperature. It might be a good idea to perhaps heat this refrigerant up a little bit more just to ensure that when it enters the compressor, it is fully a gas and there is no droplets remaining. So we superheat this refrigerant from a liquid to a gas a couple extra degrees, and that's represented by point 1 prime. As a result, the compressor input power is the same from point 2 moves over to point 2 prime because that compressor input remains unchanged. It doesn't necessarily mean we're getting more cooling capacity because the distance from point 1 to 1 prime is now larger because this increased enthalpy, the cooling load is the enthalpy multiplied by the flow rate of the refrigerant in the system. And in this case, the expansion valve has closed and it's restricting the flow of refrigerant. So the cooling load remains mostly unchanged. So the expansion valve, what it's doing is it's closing to slow the flow rate of refrigerant into the evaporator so that we get more superheat. Think of it this way. If we need more superheat, the expansion valve begins to close and it reduces the amount of refrigerant entering the evaporator. Less refrigerant in the evaporator means the refrigerant can become a gas more quickly. Once it becomes a gas, the remaining energy, or the cooling load in this case, is used to superheat the gas. It's still in its gas state. If our superheat is too much, we are wasting energy. The expansion valve has restricted the flow of refrigerant and it's impeding the compressor operation. So the expansion valve will open to allow a little bit more liquid refrigerant to enter the evaporator. And this means you'll get more evaporation, less energy left over for superheat, and the superheat will decrease. One thing to note is when the expansion valve closes is it will back up liquid refrigerant into the condenser. And this will also result in a change to the system, or subcooling, which is the difference from 0.3 to 3 prime. Similar to superheat, subcooling is the number of degrees below the saturation point of becoming a liquid, typically somewhere around 5 degrees Fahrenheit. So how do we measure superheat? Well, we can measure the temperature in the evaporator, P evap, and we can also measure the temperature at 0.1 prime. Say, for example, the pressure in the evaporator is measured at 20 psi and the measured temperature at 0.1 prime is 30 Fahrenheit. Well, using this dome, we know that 0.1 is on the saturation point, and so we can look that up in the table for this refrigerant type. And we can look up and find that at the measured pressure at 20 psi, the saturation temperature, where it becomes complete gas, is 23 Fahrenheit. And again, we've measured the temperature at that point at 30 Fahrenheit. So the superheat is calculated as 30 minus 23, or 7 degrees Fahrenheit. Typically, HVAC systems operate, depending on the type of compressor, from something like 7 degrees Fahrenheit up to 15 degrees Fahrenheit. So how does the expansion valve really work? Some basic devices like a mini fridge, they just have a fixed orifice or a tiny tube that just forces the refrigerant through, and it doesn't adjust. We don't measure anything. We just continuously restrict the flow of refrigerant to ensure that there's plenty of superheat all of the time. Well, this is not the most efficient method. It is certainly the most simplistic. So the next best way is to use a thermal expansion valve, or a TX valve. And this is a mechanical device that's shown in this image. There is a sensing bulb which contains a small amount of refrigerant or gas liquid mixture inside of it. And this bulb is connected to the suction line entering the compressor. And when the suction temperature increases, this liquid will boil and it will go through this capillary tube and enter this diaphragm, and it will push this diaphragm downwards. And this will push this needle downwards and open up this valve to allow the flow of refrigerant to increase. On the other side of this diaphragm, we're exposed to point 4, which is the inlet pressure of the evaporator, which is our P evap that we've measured before. So it is the difference between the refrigerant in this bulb acting on the diaphragm and the pressure at point 4 that are going to determine how much refrigerant is metered by this valve. And this TX valve, it comes with this special refrigerant inside of it, and they're all calibrated with the spring for a particular application, a particular number of degrees of superheat for a certain refrigerant type. Some TX valves also have an equalizer port. So like we mentioned before, the pressure in the evaporator point 4 might not be exactly equal to point 1 leaving the evaporator. You might have a little bit of a pressure drop as you go through the evaporator. So this equalizer line is connected to point 1, and it measures the actual pressure at point 1 leaving the evaporator where we're trying to achieve the superheat. So that exposes the bottom of the diaphragm to the actual pressure leaving the evaporator to compensate for any pressure drop through the evaporator. Nowadays, many systems are moving towards an electronic expansion valve where the suction pressure and suction temperature are measured with electronic devices, and then the valve is controlled with an electronic solenoid motor, and this has a pre-programmed curve or dome for this refrigerant, and the computer automatically determines how much superheat there is and if we need to meter in more or less refrigerant. So now with the understanding of the refrigeration cycle, we can go into further details on the components. Next, we'll discuss various compressor types and technologies, starting with reciprocating compressors. Think of them as a car engine. There are multiple cylinders and pistons which move up and down to compress a refrigerant. They can typically be driven by a VFD to adjust the speed of rotation. There are also cylinder unloaders available which can deactivate individual cylinders for capacity control. Reciprocating compressors have been around for many years, and they have very robust design. They have a solid cast iron body, makes them suitable for extreme conditions, and a wide operating envelope. This is why they've been used for all kinds of applications, including low temperature applications and even high pressure applications that need heat recovery. The motor is located in this area, and it is cooled by the suction gas which enters this port here, and this is why we refer to them as a hermetic compressor, because the motor is hermetically sealed within the compressor and it is cooled by the suction gas. Now this compressor we refer to as a semi-hermetic compressor because, as you can see on the body, there are nuts and bolts. We can remove this body, we can remove the motor and service everything. So we refer to it as a semi-hermetic compressor. We also refer to these as a positive displacement compressor. The easiest way to think of this is, imagine if we stopped the rotation of the compressor or the pistons. The refrigerant won't be able to go backwards through the compressor because it's always being blocked by the pistons and the valves on top of the pistons. So that's why I refer to it as a positive displacement compressor. We'll talk about other types of dynamic displacement compressors as well. And these reciprocating compressors, they're typically used for small 1 ton up to medium size applications, perhaps 80 tons out of a single compressor. Scroll compressors have become some of the most popular due to their low cost. The refrigerant enters in the suction port, and there are two scroll impellers, one of which is stationary and the other one orbits, and the refrigerant is pulled as the scrolls orbit into the center where it's fully compressed and then discharged. The motor is inside the housing, and so we call it a hermetic motor. And as you can see, this is one case that is fully welded, so it's typically referred to as a fully hermetic motor. Most of them are used as a basic on-off configuration with no capacity control, but many can also be used with a VFD driven motor for capacity control. And these are typically used for small applications, 1 ton out of 50 tons total out of a single compressor body. And the compressors are also similar to the semi-hermetic reciprocating. They are positive displacement, which means the refrigerant could not flow backwards through the scroll if the compressor was turned off. Screw compressors, they utilize two moving screw-like impellers which drive the refrigerant along their axis, and they're typically more costly to manufacture because they require a gearbox assembly to drive the screws. They can be used with a VFD for capacity control, but they're also, many of them have existed with a slide valve which exposes a certain length of the impellers in order to adjust the capacity control. Typically, they are a semi-hermetic design with the motor being located internally to the compressor. Most of the time, these compressors are available in sort of medium applications, larger than 80 tons of cooling from a single compressor. And like the other compressors we talked about, they are also positive displacement. So unlike all the other compressors we talked about, centrifugal compressors are dynamic displacement. Think of them as a fan. So we have in this case two impellers here. It's a two-stage compressor, two sets of fans. If I were to stop the compressor, impeller refrigerant could flow backwards through the compressor. So this is why we call them dynamic displacement. They can't develop as much pressure rise or lift, as we call it, on the compressor, but they are very, very efficient. And the capacity control can be done by a VFD on the motor, or also what's shown here is inlet guide vanes. And these are essentially motorized dampers that can deflect the refrigerant as it enters the compressor to adjust the capacity. And these compressors are used for large applications, typically greater than 200 tons, and many exist with 1,000 tons of capacity from a single compressor. We discussed the evaporator and condenser within the vapor compression cycle, and these are the different types of heat exchangers that typically exist within the system. They come in multiple forms depending on the application. Sometimes we're trying to cool a fluid like water, other times we're trying to cool the air. Shell and tube heat exchangers are very common. The water flows inside the tubes and the refrigerant flows around the tubes. And the tubes are typically made from copper for good heat transfer. If the water is dirty, this heat exchanger can be opened at the end and the tubes can be cleaned, which is an important feature when using them for cooling tower applications. Brazed plate heat exchangers use a series of stainless steel plates. These plates are stamped so they have dimples and the plates are sandwiched together, and the dimples create gaps in between the plates where the fluid is able to flow. A brazing compound, typically copper, is used to melt the plates together. When the refrigerant passes through the alternating sides of the plates, This is an example of a water-cooled packaged air conditioner. It's designed to cool air while rejecting the heat to some water loop. Let's try to identify some of the components. Air is drawn in through the back of the unit, and the fans in this case blow the air upwards. This unit has a DX evaporator coil, which we can identify because of the unique capillary tubes which are connected to our expansion device. Looking below, we can see the two compressors, and they appear to be a semi-hermetic reciprocating type. And we can also identify the two shell and tube condensers, and it's obvious that these are water-cooled condensers because we can find, in this case, a stainless steel water connection to these condensers. Aside from these refrigeration components, we also worth pointing out here that there are electric heaters mounted on the discharge of the fans themselves, and some electrical components as well, which make up this air conditioning unit. In this example, we're looking at a water chiller, and based on the appearance of the compressors, we can determine that they are a screw-type compressor. We have multiple shell and tube heat exchangers. So the first shell and tube heat exchanger near the top is the evaporator, and the way we can tell this is because we can see there's some insulation on the evaporator, and the suction lines from that evaporator are also insulated. So like the rule of thumb is if it's insulated, it's probably on the cold side of the refrigeration circuit. We also have two shell and tube condensers on the bottom of this machine. In this particular case, we have two compressors, two circuits, two separate shell and tube condensers, and this particular evaporator is a single evaporator unit, but it has dual circuits inside. And aside from refrigeration components, also worth pointing out the electrical panel which makes up this water chiller. Here are some typical temperature and flow rates for water chillers. Heat transfer is a function of the heat capacity of the fluid, the flow rate, and the delta T. For standard water, the BTUs per hour is 500 times GPM times the delta T. For standard comfort cooling conditions for water chillers, we have 44 degree supply, 54 return, a 10 degree delta T, and this ends up being 2.4 GPM per ton with 12,000 BTUs per ton. On the condenser side, standard conditions call for 85 degrees entering the condenser and 3 GPM per ton of cooling. This gives you an approximate 95 degree return, or leaving the condenser, and an approximate 10 degree Fahrenheit. Note that 3 GPM per ton is about 25% larger than 2.4 GPM per ton. This 25% represents the additional heat that is rejected to the condenser due to the heat of compression. Recall that the heat of rejection is the sum of the evaporator load plus the heat of compression. So 2.4 GPM represents the evaporator load, and the additional 0.6 GPM per ton represents the additional flow needed for the heat of compression. This additional 25% is an approximation. Its exact number will depend on the efficiency of the compressor and other operating conditions. There are exactly 12,000 BTUs per ton absorbed in the evaporator and approximately 15,000 BTUs per ton of heat rejection in the condenser. This is an example of an air-cooled chiller. It's still considered a water chiller because it ultimately produces chilled water, but instead of a water-cooled condenser, it has an air-cooled condenser. We know that this is DX air coil and not an evaporator coil because it does not have the unique distributors that and capillary tubes that evaporators have. The compressors are located inside this sheet metal enclosure. Fortunately, we can't see them. We can identify the brazed plate evaporator. It is again insulated and it is rectangular in shape, which would indicate it is a brazed plate evaporator. In this example, we also have these insulated cylinders. So they're probably not condensers because they're insulated. We also don't have any water piping going to them, but I can tell you in this case they are what are called liquid receivers. And we can cover that in the more advanced Refrigeration 102 seminar. This is a good example of a water-cooled chiller because most of the components are easily visible for you to see. At this point we can quickly identify the reciprocating compressor, we can identify the brazed plate evaporator, and we can identify the shell and tube condenser. We know it's a condenser because it's non-insulated. And then we can also follow the water piping here into the end of the condenser. So let's try to identify some of the refrigerant lines and follow those. The easiest place to start is with the compressor. We have the suction line, and again that's the low temperature, low pressure side, so we expect it to be insulated. And we have the discharge line, which is a high pressure, high temperature side, and it's non-insulated. This discharge line runs along here, in case it's not obvious, and down into the condenser. Leaving the condenser, we then have the liquid line, and this runs upwards into the liquid line solenoid valve, filter dryer, liquid line sight glass, and again we'll talk about those in a Refrigeration 102 class. And the liquid line runs into the expansion device, which you can just see in behind there. That expansion device is attached to the inlet of the evaporator. So I hope this photo and the other ones help illustrate the components of the refrigeration system in the field. So this is the end of the presentation. I hope that this presentation helps people get a handle of refrigeration as a concept and to internalize the concept of refrigeration. For those who already know about refrigeration, it's a good brush up. I also hope that it was valuable in terms of identifying components and real-world examples. And stay tuned for the Refrigeration 102 class, where we will go over advanced components of refrigeration, like we touched on the components inside the refrigeration lines, liquid receivers, low ambient control, head pressure control, and many more intermediate level subjects. So thanks again for tuning in.